Imagine standing on the edge of the universe, gazing into the infinite void, where the laws of physics tease possibilities that defy our wildest dreams. Stars that pulse with the energy of the vacuum itself, holes in space-time that spew light instead of swallowing it, and entire universes dancing just beyond our reach. These are the unproven wonders of the cosmos, ideas born from equations that whisper truths we've yet to see with our own eyes. Science has always been a dance between the proven and the possible, a delicate waltz where hypotheses lead and evidence follows. Sometimes it takes centuries for the two to align, as they did with black holes, first imagined in the 18th century and only confirmed in 1971. Today we're diving into the uncharted waters of theoretical astrophysics, exploring exotic stars, white holes, wormholes, and the tantalizing idea of a multiverse. Buckle up, because this journey through the cosmos will stretch your imagination, spark your curiosity, and leave you wondering, what else is out there, waiting to be discovered? Let's inspire each other to ponder the unknown. Hit that like button if you're ready, and share your thoughts in the comments below as we embark on this cosmic adventure together. Stars have always been humanity's beacons in the night sky, their fiery hearts illuminating the darkness and forging the elements that make up our very existence. Through violent thermonuclear reactions, they cast light across the cosmos, warming planets and seeding the universe with the heavy elements that form everything from mountains to our own bodies. We've learned so much about stars, how they're born, how they live, and how they die. We can even predict that in about 5 billion years, our sun will exhaust its hydrogen fuel, swell into a red giant, and eventually collapse into a white dwarf, a stellar remnant held up by a strange quantum force called electron degeneracy pressure. But what if there are stars out there that don't follow these rules? Stars so bizarre they seem to belong to the realm of science fiction, yet are rooted in the equations of physics. Let's explore one of the strangest possibilities. A star made not of matter as we know it, but of the very vacuum of space itself. To understand these exotic stars, we first need to grasp how ordinary stars work. Take our sun, a massive sphere of plasma held together by a delicate balance. Gravity pulls its gases inward, trying to crush it, while the radiation from fusion reactions in its core pushes outward, keeping it stable. This tug of war between gravity and pressure defines every star we know. In the sun, the pressure comes from fusing hydrogen into helium, releasing energy that lights up our world. When the hydrogen runs out, the sun will fuse helium into heavier elements like carbon and oxygen, becoming a red giant. Eventually, when no fuel remains, it will collapse into a white dwarf, where electron degeneracy pressure, a quantum effect that prevents electrons from squeezing too close together, holds it up. But what happens when a star's core is so massive that even this quantum pressure isn't enough? If it exceeds the Chandrasekhar limit, about 1.4 times the sun's mass, the core collapses further, triggering a supernova and potentially forming a neutron star, where neutron degeneracy pressure takes over. These are the densest objects we know, save for one thing: black holes. Black holes form when a star's core exceeds even the neutron star limit, around 2.2 times the sun's mass. Here, gravity overwhelms all known pressures, collapsing the star into a point of infinite density, a singularity, hidden behind an event horizon from which nothing escapes. But what if there's something beyond this? What if there are stars made of matter so exotic that they defy these limits? Stars that could be smaller and denser than neutron stars, yet still avoid collapsing into black holes. This is where the idea of a gravitational vacuum star, or gravastar, enters the stage, and it's as mind-bending as it sounds. In 1959, physicist Hans Adolf Buchdahl showed that any realistic star made of matter with positive energy density and pressure must be at least 9/8 times its Schwarzschild radius, the size at which it would become a black hole. But what if a star could have negative pressure in some regions? Negative pressure is a strange concept. It's not about having fewer atoms than zero, but about a force that pulls inward rather than pushing outward, like a cosmic suction. In the 1930s, physicists Tolman, Oppenheimer, and Volkoff developed the TOV equation, which describes how pressure changes within a stable star. For a star with negative pressure at its core, the equation predicts something extraordinary. The pressure must spike to negative infinity somewhere inside, then flip to positive infinity before dropping to zero at the surface. But there's a special case where this gets even weirder. If the pressure at the center is exactly equal and opposite to the star's energy density, the pressure and energy remain constant throughout the star. creating a bizarre object where gravity and pressure cancel out perfectly. This object, called a gravastar, has properties that sound like something out of a cosmic fairy tale. Its interior is a perfect vacuum. No gravitational pull, no pressure gradients, just a serene void where you could float freely, as if in empty space. Yet this vacuum has a positive energy density paired with a negative pressure, eerily similar to dark energy, the mysterious force driving the universe's accelerated expansion. Could gravastars be made of dark energy? If so, they might hold clues to one of the biggest mysteries in cosmology. Even more intriguing, gravastars can be arbitrarily close to their Schwarzschild radius, making them nearly indistinguishable from black holes. This poses a challenge for astronomers. Every time we think we've spotted a black hole, could it actually be a gravastar masquerading as one? To tell them apart, scientists look for one key difference. Black holes have event horizons, surfaces from which nothing escapes, while gravastars, being slightly larger, do not. This means gravastars could emit light or other signals, unlike black holes. Gravitational wave observatories like LIGO can also help, as the waves from a gravastar merger might differ subtly from those of a black hole, but the resemblance is so close that even with our best instruments, distinguishing them is a daunting task. In 2023, a study from the University of Hawaii suggested that massive black holes might be growing at the same rate as dark energy's influence, hinting that they could be gravastars filled with dark energy. This idea sparked fierce debate, with astronomers questioning the data and theorists arguing that black hole growth shouldn't tie to cosmic expansion. The jury is still out, but the possibility that gravastars could be the dark energy driving the universe apart is a thrilling prospect. What do you think? Could these vacuum stars be hiding in plain sight? Share your thoughts in the comments, and let's keep this cosmic conversation going. If gravastars push the boundaries of what we believe stars can be, our next cosmic marvel flips the script entirely. Picture a black hole, a region of space-time so dense that it swallows everything, even light, trapping it behind an event horizon. Now imagine its opposite. A white hole, a cosmic fountain that spews light and matter into the universe while allowing nothing to enter. It sounds like science fiction, but the mathematics of general relativity suggest white holes are just as plausible as their dark counterparts. To understand them, let's dive into the geometry of space-time and explore why white holes might be more than just a theoretical curiosity. Think of a cone. In the real world, you might picture a traffic cone pointing up or an ice cream cone pointing down. But mathematically, a cone is two halves joined at their tips, one pointing up, one down. Black holes are like the ice cream cone half. We're familiar with them as the remnants of collapsed stars, defined by their event horizons. In a Penrose diagram, a tool physicists use to map space-time, a black hole appears as a region where light and matter can enter but never escape, doomed to hit a singularity in the future. But the full mathematical description of a black hole, one that assumes it's existed forever without forming from a star, reveals something more. A white hole, the traffic cone half, where light and matter can exit but never enter, connected to a singularity in the past. This symmetry is stunning. The same equations that describe black holes predict white holes, suggesting they're two sides of the same cosmic coin. In the Penrose diagram, the black hole, region 2, sits alongside our universe, region 1, separated by the event horizon. The white hole, region 3, mirrors it, allowing light to escape into a parallel universe, region 4, disconnected from our own. This doesn't mean every black hole has a white hole attached, just as not every cone in the real world has both halves. But it does mean white holes are consistent with physics, even if we haven't spotted one yet. Why haven't we? One possibility is that white holes are unstable, forming and dissipating quickly in the early universe. Another is that they're out there, hiding in plain sight, waiting for us to develop the tools to detect them. One intriguing hypothesis ties white holes to the death of black holes. Black holes aren't eternal. They slowly lose mass through Hawking radiation, a quantum process where particles escape near the event horizon. When a black hole shrinks to the Planck mass, about 20 micrograms, our theories falter. Enter loop quantum gravity, a framework that tries to merge quantum mechanics with gravity. It suggests that at this tiny scale, a black hole might quantum tunnel into a white hole, releasing its contents over time. This white hole, though small, could hold vast entropy due to its stretched internal geometry, potentially solving the information paradox, a decades-long puzzle about whether information lost in a black hole is truly gone. As the white white hole fades, it flattens space-time, ending its cosmic journey. Here's where it gets wild. Our universe itself might be a white hole. General relativity describes the Big Bang as a singularity in the past, much like a white hole's past singularity. Loop quantum gravity hints that our expanding universe could have emerged from a collapsing one, a white hole born from a black hole's ashes. This idea challenges everything we think we know about our cosmic origins. Could we be living in the aftermath of a white hole? Let's ponder that in the comments. What's your take on this mind-bending possibility? And if you're as fascinated by these cosmic mysteries as I am, hit that subscribe button to join our journey through the universe's unproven wonders. If white holes stretch our understanding of space-time, wormholes take it to another level. Imagine a tunnel connecting two distant points in the universe, or even two different universes. This is the realm of wormholes, hypothetical bridges in space-time that could link far-flung regions or parallel realities. They too emerge from the mathematics of general relativity, particularly in the context of spinning or charged black holes, where the geometry of space-time gets even stranger. Let's revisit the Penrose diagram, but this time for a spinning black hole. Unlike the simple stationary black hole with its inevitable singularity, a spinning one has a more complex structure. The diagram now shows 8 regions, repeating infinitely. Regions 1 through 4 are familiar: our universe, the black hole, the white hole, and a parallel universe. But the spinning black hole introduces new regions, 5 through 8, where space-time behaves differently. As you cross the event horizon, you're drawn toward the center, but you soon reach an inner horizon where space-time unwarps. Here you could float freely, even touch the singularity, a ring, not a point due to the black hole's spin. This region is a wormhole, a passageway that could lead to another universe or back to a white hole in a new reality. The catch? Wormholes are fragile. Disturbing their delicate structure, say by passing through, might cause them to collapse. Plus, the path around a spinning black hole's ring singularity could lead to causal paradoxes like visiting your own past, which general relativity struggles to resolve. These issues suggest that wormholes, while mathematically possible, might not exist in stable form in the real world. The turbulent collapse of stars into black holes violates the assumptions of perfect symmetry in Penrose diagrams, and general relativity itself may break down near singularities, where quantum effects dominate. Yet the idea of wormholes captivates us, fueling dreams of interstellar travel or glimpses into other universes. Share your wildest wormhole theories in the comments. Let's see how creative we can get. Our journey through exotic stars, white holes, and wormholes brings us to perhaps the most audacious idea of all, the multiverse. Why does our universe seem perfectly tuned for life? The dark energy density, a measure of the force driving the universe's expansion, is astonishingly small, about 10 to the -9th joules per cubic meter. If it were much larger, galaxies, stars, and even atoms might never have formed, leaving a barren cosmos. If it were negative, the universe would have collapsed in a big crunch. Quantum field theory predicts a dark energy density of 10 to the 45th joules per cubic meter, a number so large it's off the charts. How did we get so lucky? One explanation is the multiverse, a collection of universes with different physical constants. In 1987, physicist Steven Weinberg used the anthropic principle to argue that we can only observe universes where life is possible. If countless universes exist, each with a random dark energy density, we'd naturally find ourselves in one where the value is just right, around 10 to the -9th power J per cubic meter, low enough for galaxies to form. This isn't about coincidence or design, it's about probability in a cosmic lottery. With enough universes, even the improbable becomes inevitable. Physicists propose several types of multiverses. One is temporal. If the universe cycles through big bangs and big crunches, each iteration might have different constants. Another is spatial. Regions of space beyond our observable universe might have different laws. A third, from the many worlds interpretation of quantum mechanics, suggests that every quantum event splits the universe into multiple branches. Each model offers a way to explain our universe's fine-tuning without invoking a higher power. But there's a catch. We have no direct evidence for other universes. Observing them would require surviving a big crunch, reaching unreachable parts of space, or crossing quantum barriers, tasks that seem impossible. Yet the multiverse remains a compelling hypothesis, supported by the same logic that predicted black holes long before we saw them. Beyond gravastars, another class of exotic stars beckons us into the unknown: strange matter stars, or quark stars. These hypothetical objects push the boundaries of stellar physics even further, proposing that under extreme conditions, matter itself transforms into something entirely alien. Neutron stars, as we know, are held up by neutron degeneracy pressure, but what if the pressures and densities inside a star's core were so intense that neutrons themselves broke down? In this realm, quarks, the fundamental building blocks of protons and neutrons, could roam freely, forming a soup of strange matter, a state where up, down, and strange quarks coexist in equal measure. This strange matter is theorized to be more stable than ordinary nuclear matter, potentially allowing stars to exist in a state denser than neutron stars, but not quite collapsed into black holes. The idea is tantalizing: a star made of pure quark matter, glowing with the energy of a cosmic crucible, challenging everything we know about stellar evolution. The journey to understanding strange matter stars begins with the collapse of a massive star. When a star's core exceeds the neutron star limit, it faces a choice: collapse into a black hole, or perhaps stabilize as a quark star if strange matter is indeed more stable. The equations governing this transition are murky, as our understanding of quantum chromodynamics, the theory of strong nuclear forces, struggles at these extreme densities. Yet some models suggest that a neutron star's core could convert into strange matter, creating a hybrid star with a quark core surrounded by a neutron crust, or even a fully quark star. These objects would be incredibly dense, potentially smaller than neutron stars, with surfaces that emit bizarre radiation patterns due to their unique composition. Detecting them is a challenge, as their gravitational signatures might mimic those of black holes or neutron stars, but subtle differences in their pulsar signals or gravitational wave emissions could betray their existence. Imagine the thrill of spotting a pulsar with an unusual spin pattern. Could it be a quark star? Let's discuss in the comments. What kind of experiments could we design to hunt for these cosmic oddities? The implications of strange matter stars extend beyond astrophysics into the realm of particle physics. If strange matter is stable, it could exist in tiny nuggets called strangelets, which might have been created in the early universe or in high-energy cosmic collisions. These strangelets could drift through space, occasionally colliding with neutron stars and triggering their conversion into quark stars. This raises a provocative question: could strange matter be contagious, spreading through the cosmos like a cosmic wildfire? The idea is speculative, but it underscores the interconnectedness of the universe's mysteries. A single quark star discovery could rewrite our understanding of matter itself, bridging the gap between the infinitely small and the cosmically vast. As we peer into the night sky, let's keep our eyes open for these strange stars. Share your thoughts on what finding one might mean for science. While gravastars and quark stars challenge our view of stars, another unproven phenomenon takes us back to the universe's infancy: primordial black holes and their potential white hole counterparts. Unlike black holes formed from dying stars, primordial black holes are theorized to have formed in the chaotic moments after the Big Bang, when dense pockets of matter collapsed under their own gravity. These black holes could range from microscopic to massive, with some theories suggesting they could account for a portion of the universe's dark matter. But what if some of these primordial objects were white holes instead? Born in the same fiery crucible, primordial white holes could have spewed matter and light into the early universe, shaping its evolution in ways we're only beginning to understand. Their fleeting existence, potentially evaporating quickly due to Hawking radiation, makes them elusive, but their fingerprints might linger in the cosmic microwave background or gravitational wave signals. Detecting primordial black or white holes is a cosmic treasure hunt. Their small size and ancient origins mean they wouldn't resemble the massive black holes we observe at galactic centers. Instead, they might manifest as brief bursts of gravitational waves or unexplained gamma ray signals. As of August 31st, 2025, data from observatories like LIGO and the Fermi Gamma Ray Space Telescope have hinted at anomalous events that could align with primordial black hole mergers, but no definitive evidence exists. For white holes, the challenge is even greater. Their outward flow of matter might mimic other explosive phenomena like supernova or gamma ray bursts, yet their unique signatures, such as a lack of an event horizon or specific light emissions, could set them apart. Imagine the excitement of detecting a signal from a primordial white hole, a relic of the universe's first moments. What kind of technology do you think we'll need to confirm their existence? Drop your ideas in the comments and let's brainstorm together. The possibility of primordial white holes also ties back to our universe's origin story. If our universe emerged from a white hole, as some loop quantum gravity models suggest, primordial white holes could be miniature versions of that cosmic birth. They might have seeded the universe with matter, influencing the formation of the first galaxies. Some theorists even propose that these white holes could connect to primordial black holes via tiny wormholes, creating a network of cosmic tunnels in the early universe. Such a network could explain anomalies in the distribution of galaxies or the cosmic microwave background's temperature fluctuations. As we refine our telescopes and simulations, we edge closer to testing these ideas. The thought that our universe might be dotted with these ancient relics is awe-inspiring. Let's keep the conversation going about how we might find them. Beyond the realm of exotic stars and space-time tunnels lies another theoretical oddity that challenges our understanding of the cosmos: naked singularities. Unlike black holes, which hide their singularities behind an event horizon, a naked singularity is a point of infinite density exposed to the universe, with no barrier to shield it. General relativity predicts that singularities form when massive stars collapse, but the cosmic censorship hypothesis, proposed by Roger Penrose, suggests that nature forbids naked singularities, always cloaking them in event horizons. Yet certain extreme conditions, like a rapidly spinning star or specific charge configurations, could in theory strip away this cloak, leaving a singularity bare. The implications are staggering. A naked singularity could emit information freely, defying the isolation of black holes and potentially allowing us to probe the quantum nature of gravity itself. The existence of naked singularities would rewrite the rules of physics. They could act as cosmic beacons, emitting unpredictable radiation or gravitational effects that differ from black holes or other compact objects. Detecting them would require observing anomalies in gravitational wave signals or unusual light patterns that don't match known phenomena. As of August 31st, 2025, no confirmed naked singularities have been found, but recent advancements in gravitational wave astronomy, such as the upgraded LIGO-Virgo network, have heightened our sensitivity to such anomalies. The challenge lies in distinguishing a naked singularity from other exotic objects like quark stars or gravastars, which also produce unique signatures. If we found one, it could unlock secrets about the universe's most extreme conditions, offering a window into the breakdown of general relativity. What would discovering a naked singularity mean to you? Share your ideas in the comments. Let's imagine the cosmic revelations it could bring. At the smallest scales of the universe, where quantum mechanics and gravity collide, another unproven wonder emerges: the Planck star. Proposed as a solution to the black hole information paradox, a Planck star is a hypothetical object that forms when a collapsing star reaches the Planck length Planck scale, the realm where spacetime itself becomes quantized. Unlike a singularity, which implies infinite density, a Planck star suggests that quantum effects halt the collapse, creating a dense but finite core. This core, stabilized by quantum gravity, could exist within a black hole, replacing the singularity and preserving information that would otherwise be lost. As the black hole evaporates via Hawking radiation, the Planck star might eventually emerge, potentially transforming into a white hole or releasing its contents in a final burst, offering a resolution to one of physics' greatest puzzles. The idea of Planck stars pushes us to the edge of our theoretical understanding, where general relativity and quantum mechanics must reconcile. Detecting them is a monumental challenge, as their effects would be most pronounced at scales far smaller than our current instruments can probe. However, their influence might manifest indirectly, perhaps in the final moments of a black hole's evaporation, producing detectable bursts of high-energy particles or gravitational waves. As of August 31st, 2025, experiments like the Event Horizon Telescope and future quantum gravity observatories are laying the groundwork for testing these ideas, but we're still far from confirmation. The prospect of Planck stars invites us to rethink the nature of reality itself, blending the cosmic with the quantum. What do you think a Planck star discovery would reveal about the universe? Drop your thoughts in the comments and let's explore this quantum frontier together. From gravastars to white holes, wormholes to multiverses, the unproven wonders of the cosmos remind us how much we've yet to discover. Black holes were once just equations on a page, dismissed as mathematical curiosities until Cygnus X1 was spotted in 1971. Today's hypotheticals could be tomorrow's realities. The universe operates on rules so consistent that our equations can predict phenomena we've never seen, like a cosmic Sherlock Holmes unraveling nature's mysteries. This is the thrill of science. science, to imagine, to calculate, and to chase the unknown. As we stand on the brink of these cosmic possibilities, let's embrace the wonder of it all. What do you think lies beyond our telescopes? Could gravistors be the key to dark energy, or white holes the remnants of dying black holes? Might wormholes connect us to other universes, or does a multiverse explain our existence? Share your thoughts, your hopes, and your wildest cosmic theories in the comments below. Let's keep this conversation alive, inspire each other, and maybe, just maybe, catch a glimpse of the next great discovery. If this journey through the cosmos has sparked your curiosity, hit that like button and subscribe for more adventures into the unknown. Together, let's keep exploring the unproven wonders of the universe, one star at a time.